Yes, welcome to Space Sciences, Session 5 on day 2. Dmitry, we were going to let Carl kick off with the James Webb Space Telescope and then follow up with you. You'll be the second speaker in our trio on your Apache Point exciting project, the Sloan Digital Sky Survey. And then I'll finish up with synthetic tracking of asteroids. And I have, we're kind of changing the order a little bit because that will give me the ability to shorten or lengthen my presentation based on how much time we have if I'm coming in with the caboose. Because I wanted to, if we have time, I want to share software.
Do we have 15 or 20 minutes per presentation?
20 minutes.
Okay.
The session goes till 12:40. So we'll shoot for 20 minutes, 15 to 20 minutes in that range.
Okay.
And I'm showing 11:31. My name is Dr. Ed Albin. I'm a speaker in the session, and I'll also be moderator for the session. I'm program director for space studies at the American Public University System. And we have about 9 or 10 folks in. We'll give them another minute or two before we get underway. And I will introduce our speakers before their presentation, but just briefly, we have Carl Starr, who is the program manager for missions operation manager for NASA's James Webb Space Telescope. He's at the Goddard Spaceflight Center, NASA's Goddard Spaceflight Center, and Dmitry Bizyaev. Did I pronounce that correctly, Dmitry?
That's okay.
Okay, because I always botch your last name. Apologies. As people do my last name as well. Dmitry is the deputy lead astronomer for the Apache Point Observatory in Sunspot, New Mexico, observational astronomer who has been heavily involved in the Sloan Digital Sky Survey, mapping galactic distribution in our cosmos. And let's see. Okay, we've got 14 participants. Again, welcome everybody to Space Sciences, Session 5. We have 3 presentations today. Carl Starr will be talking about the James Webb Space Telescope mission, the preparing for launch in a pandemic, and Dmitry will be discussing the Sloan Digital Sky Survey, current state and perspectives, survey of the universe. And I'll round up our talks today with discussion of synthetic tracking of near-Earth and main belt asteroids using an interesting software package called the Tycho Tracker. It's a new synthetic tracking software package if you're interested in doing follow-up observations of asteroids and perhaps discovery of near-Earth and main belt asteroids. A lot of opportunity there. All right. Okay, so I'm showing 11:34, and we'll get underway. And let me introduce our first speaker. Our first speaker is Carl Starr. Again, he is the NASA's Missions Operations Manager at Goddard Spaceflight Center for the James Webb Space Telescope, JWST as we call it. Carl spent his early career in the 12 years in the Army Space Command, and with his experience, he went on to to work intimately with the Chandra X-ray Observatory, and also spent time with Northrop Grumman with their EOS satellite systems, the Aqua and Aura satellites. So with this experience, as well as having degrees from the American Public University, his bachelor's and master's degree in space sciences, Carl landed a job as a senior systems engineer for the James Webb Space Telescope for a very long period of time. He's been working with this exciting telescope. It's not a replacement for Hubble. It's above and beyond what Hubble will do, as Carl will describe. And now he is the missions operation manager at the Goddard Spaceflight Center. And his talk today is the James Webb Space Telescope preparing for launch in the pandemic. And I'm really excited about JWST getting into orbit very, very soon. So without further delay, Carl Starr.
All right. Thanks, Dr. Albin. Appreciate it. Let me go ahead and share my screen. All right. Is that showing okay?
Got it. Looks
okay,
good.
Great. Well, thanks for having me. I really appreciate it. I have a lot of information. It's pretty dynamic across the board about what I'll talk about. So if there are questions, just go ahead and use the chat room or post your question there, and I'll do my best to look for that. So maybe, Dr. Albin, if a question pops up, just give me a hand up or something. I can see you, but I can't see the other icons. So if somebody has a question or they post something, always a good time to stop and just address it right there. No problem. No problem.
Absolutely, Carl.
All right. Okay, so let's see if so I'll give a little quick introduction. I'll give you a little overview of the telescope, and then I want to kind of jump into the impacts, basically, of the pandemic, physical limitations that we have, workforce changes, how the concept of operations change, and what you have to do there, how you plan forward in a pandemic, and then I'll just conclude with some concluding thoughts. So as Dr. Albin said, I had spent 12 years in the service, in Army Space Command, and then right out of there went to work on the Chandra telescope. I think running my own business for some years and working with engineers and other staff allowed me to see different sides of the industry. So that was really good, and I appreciate all that time. But for the last 6 years, as he said, I've been the mission operations manager. And so basically what that means is I'm responsible for all the operations on the telescope once we separate from the launch vehicle, which is about 30 minutes after it launches. So there's a whole team on the ground at the launch site, and after launch, once the rocket goes away, then everybody kind of falls underneath me, which is, you see here on the second to the last bottom bullet. It's I have a team of about 600 engineers and scientists that it takes to commission it and move the mission along for the James Webb Space Telescope. And also, I am a graduate of APUS in space studies at the time, so I always am looking to help fellow students and alumnus who want to either come up to the control center or talk about how they get into the industry and what the industry is bringing, what people look for when they are when they're hiring. We do hire quite a bit, so I'm always some of the people that we've helped are in the mentoring program. So I'm also a mentee with the university, and I've brought several people from that program up to the control center, and I think one of them might even want to work there. So that's always good. And then I think one of them got accepted as an internship up at the Institute. working on the telescope. So there's all kinds of possibilities. And like I said, I think it's all about the network. And so since you're connected here, just feel like you always have a personal reach into the telescope. And I'll give people that. So the telescope, obviously, you know, I like to brag about it, right? It's going to be the most powerful space complex ever built. It's very big. It's about a 2-story building. You can think it's absolutely huge. I have a slide coming up to show some dimensions of it. And it all folds up on a rocket that's going to launch out of French Guiana later, a year from now. Recently, we did complete a bunch of environmental testing, which subjects the observatory you see in the picture on the top right. It's the same picture, but it was just turned in different degrees. I showed 2 different shots of it. They take that, the observatory there, it's all folded up, and then they subject it to vibrations and things of that nature to simulate what it would experience from the rocket. And I'm happy to say nothing fell off and nothing broke. So it's all really good. And so while that team has been building the observatory, it's being built out at the Northrop Grumman facility out there in Redondo Beach, California. The operations personnel have been all the people that we work with. We've spent the last 4 years going over how to operate it. It's never been done before, so it's a unique, one-of-a-kind system. So everything has to be done from scratch. You can look at best practices, and we of course have done that over the years, but typically, it's when it's a unique, one-of-a-kind system, that means you do have to invent the wheel. You may not have to invent all the tools for that wheel, but you're going to reinvent it. So it is an amazing observatory. It's going to be awesome when it launches. And then more recently, as we're preparing for launch, we've had a pandemic, and so now what we have to do is we have to incorporate different protocols, different considerations, and that'll be the basis of what we talk about today, what that really means. So just a little bit about what the observatory is for those that don't know. It's an old picture that I have there, but it gives you an idea. So it's as Ed said, the James Webb Space Telescope is led by Goddard Spaceflight Center here in Maryland, and ESA, the European Space Agency, and the Canadian Space Agency are real big partners, right? They're partners with us on this, and then our contractors, Northrop Grumman and Ball Aerospace. We fly the telescope from the Space Telescope Science Institute. That currently is where the Hubble science mission is run. What's different about JWST is that Hubble is actually flown out of Goddard Space Flight Center, but the science mission is run out of the Space Telescope Science Institute. So following the Chandra paradigm, we put both of those aspects together, and it's all at the Institute now. So the science and the operations, all of it comes out of Baltimore, Maryland. The instruments are listed here. As you can see, it's a worldwide partnership with our European friends and also the Canadians. And I just got a little bit there on the bottom. You can see how big it is, 6.5 meter diameter. That all gets folded up. The telescope gets folded up like origami into the fairing of a rocket. I don't have a lot of time, so I don't have those pictures, but if you go to any NASA website or look up JWST, there's lots of pictures. You can see how amazing it'll be about deploying this observatory. And it's very cold. It takes us a long time to get cold, so also it's a little different kind of mission when I think the public is used to a launch and then right away they see something and right away they get data, or maybe with some of the missions out of JPL, they launch right away and then nothing happens for 6 months, and then it's very intense. This mission is a little different. We launch and it's very intense from the very first day and continues for 6 months, readying the telescope for pictures. Our first pictures won't come out for a good couple of months by design because we're a passively cooled telescope. So we operate at minus 470 degrees Fahrenheit. on one side, and the other side of the vehicle is, you see on that diagram, there's a shield in the center between the telescope and what looks kind of squarish on the bottom. That's the spacecraft. The telescope is minus 470 degrees Fahrenheit. That spacecraft portion there, separated by the sun shield, is running at room temperature. This gives you an idea of some of the technical challenges that we have. And again, we're going to launch in 2021. So, and as Ed said, it's not really a replacement, it's a successor. And what I did is I included the 4 main science themes that are popping up on the screen. You can see here that JWST is going to bring. So it's much more powerful than Hubble, but it's not really a replacement because we operate in the infrared, not visible light. So already it's a little different. We also operate out at L2. Hubble's around the Earth in a low orbit, but nonetheless, the 4 main science themes, and these have evolved over the years. First light and reionization, the assembly of galaxies, planetary systems, and the birth of stars. So there's a lot. I think a lot of people also hear about some of the exoplanet surveys that are going on, and some of the data that's already been collected. What will happen is those are being written into science proposals for JWST, and you can go off and there's instrumentation on the vehicle, a spectrometer, where you will be able to, if somebody identified an exoplanet, you could turn the telescope to James Webb on it, and with spectroscopy, you could tell what was in the atmosphere, if there's life, things of that nature. So JWST is kind of it's a partner with a lot of previous science missions that have gone out, because now with all of that data collection, now scientists know where they want to point instead of wasting time of just kind of scanning around. Okay, so that's with the telescope. And then, so now what I want to kind of do is just start talking about what the impacts are to the team and to the project. Like most projects, we lost some time when the pandemic hit. For us, we had an earlier launch date, but because of COVID, we were delayed by about 6 months. So, everybody had an impact for that. And it manifested across all the programs. During the most recent time, the only science mission that's gone up is the Mars mission that recently went up. And that's been it. There have been rocket launches, but again, no true missions have tried to launch in the pandemic. So again, we're kind of cutting our teeth and kind of going forward with, well, how has this impacted us, and what should we look out for? So what I've done is I'm going to share with you some of our lessons learned that we've got, and I broke it down into 4 areas. There's probably many ways you can slice and dice COVID, but I broke it down into 4 areas of obviously the physical limitations, and then also how the workforce has changed, the concept of operations, and planning challenges. So I'll talk about each one of those briefly. And if there's questions, again, just stop me as I go through. Okay, so let's see. You can first off see with the pictures I have here on the right, we have a very big control center up in Baltimore, Maryland. You see the top picture, there's a lot of people in there. And you see the middle picture, still a bunch of people. And now there's nobody, there's 1 person. So obviously what we've had to deal with is square footage requirements, and how does that translate into operations? So you can see what that really means, right? If you follow the best practices, you take a normal room and now you're allocating 100 to 150 square feet. You can see there in the first bullet and the second sub bullet there, we had that room that I'm showing you here in the picture easily supported 53 people in there, and now only 11 are allocated to go inside. And so what that does is it drives us to a distributed support concept. And what that means basically in short term is the control center, the Mission Operations Center for JWST in the Space Telescope Science Institute, it actually is on the 3rd floor, the north section of the 3rd floor in what's called the Muller building, the main building there. And the way that we've distributed the team now is we're just basically extending these rooms that you see here into the office structure and the whole floor. So we've taken over the whole floor almost, and are putting the engineering staff in offices. So we are running new cables, putting in different workstations. There's no more personal offices. It's now just become office space where engineers can come in, hook their laptop up, plug into the system, and it's as if they were sitting in one of those rooms that you see up above. So that has been a challenge, but that's something that I think people should want to think about if they're going to, if they have a mission that's going to require a team. What do you do with that team in the time of COVID? How do you protect that team also as you get closer, which becomes a concern, is how do you make sure you don't jeopardize your mission success if you can't tolerate somebody getting sick? Of course, what's been happening is you have to maintain a physical distance. And so what happens is people essentially are encouraged not to congregate anymore. Meetings have less face-to-face participants. So again, these are just obvious things that happen when you impose physical limitations on your workforce. This is kind of what happens. But then what you start to see, I'm bringing up on my last bullet here, is because of this, you start to realize that there's a real big importance of the eye contact versus video. Video is great, and it's obviously allowing us to do the conference today, and schools have been doing remote learning, but making eye contact is definitely one of the most valuable tools that we have, making sure everybody's on the same page. Typically, when we run our meetings at the control center, I will go around the room and I will ask all of the lead engineers and the scientists, for their input or if they had any questions or whatever it is. And you go around the room and you can kind of see just the subtle features in somebody's facial expressions. If it's just an eye twitch or maybe a smile. You can't see smiles anymore because everybody's got masks on. But you might see their eyebrows raise, their body posture change. There's things that you can see with the video. I mean, video goes so far, but that you cannot really substitute for that in person. We find that to be very valuable. A lot of times you go around and somebody just doesn't want to say something because you're in a room with all the senior NASA people and you're making decisions, and people get kind of worried about $10 billion and the fact that they got to make a decision and they want to say something, and you see that they're about to and they don't. Subtle movements allows us to go back, query them, challenge them, come back into the group, and then we can talk about that. So again, the physical limitations have caused us to rethink the workforce and how we interact with them. So it's just something I want to share with you. It's very subtle. All of a sudden you realize people are remoting, and it has impacts. So how does that workforce change? Especially in the technology area, unless you're building something, unless you're putting hardware together, a lot of people that can do their job at home are encouraged to do so. We have the same philosophy on our program. And what we noticed over the last 6-7 months is that even though that we're still productive from a people point of view, we notice, some of the problems, of isolation start setting in, and we realized that some of that team aspect was suffering a little bit. And so that's very hard to overcome that. It's just, I don't know that it's solvable, but it's something to be aware of, is that when you go into a full remote environment, you really need to make sure that you communicate. You try to find in person, but a lot of times it's impossible now. So, video conferencing is what we rely on to try to establish some kind of human contact. And then on our program, we do video first, then we'll telephone as much as we can, of course. But then texting, we try not to, it is efficient. And I think the workforce today that comes right out of school and the people entering the workforce are very adept at texting, and it works well. But to hold a team together, it's not the right tool to do that. It's a good tool to use, but as all tools, right, has its own particular function.
Carl, we have a question for you here. if this is a good point to
Yeah.
interject. David Engelman is asking, well, he mentions a good point that it's been proven that under telework conditions, folks actually work more hours. And he's asking, have you seen any efficiencies or increased productivity due to this construct of doing teleworking?
Yes, that's a great point. So we do recognize people work more. However, the inefficiency, I think, that we see is that even though you are able, you seemingly do work more, or you're plugged in more, that workday becomes spread across 24 hours versus a normal work day that typically gets answered from 8 to 4 p.m. or something like that. What happens is, again, you have to allow for real life to go on, and the people are working longer hours, but they may not be able to respond back to you until after they've done caregiving at home, or they've taken care of some scholastic thing with children if they have them. People that don't have children may have other obligations or things that they do. So it's, don't misinterpret. I don't mean to say remote is bad. It is what it is. It's here. And it works. Like I said, we continue to function. I'm just trying to point out that you need to be aware of what you lose with remote. You may not lose productivity. You may keep it. You may be able to take the efficiency hit, but what happens is keeping a team together, team building, those become very hard to do. Very hard to do. I hope that answers that question. Whoops, what did I do there? Hit the wrong button. Let's see, another thing that happens that I think people did not plan on is, we have to actually change the job descriptions from your HR department. That's something that people should think about, because now some work is requiring you to be at a place of work, and that can be difficult to do with a lot of concerns that are going now in the pandemic. And also what we found out is that you need more support and resources, because you need now extra people to help you with logistics of keeping people separate, new administrative tasks. Maybe you need to have a brand new website that talks about COVID protocols. We have seen lots of new people pop up doing jobs that were never there before, because now you have to do them in the time of a pandemic. Somebody there taking your temperature, somebody handing you a mask, etc. Right? These things manifest into the workplace. Your concept of operations is going to change. What does that mean? For example, you're limited in number of people. And so now you have to go back kind of to square one of, well, what do I really need to do this? Do I really need 2 people, or can 1 person do it? And if 2 people are needed, why do I need 2? Why not 3? It's also caused us to redefine certain words. For example, on remote versus virtual. You can support remotely, which means that you're at a designated place that we can rely on your network. But virtual is, basically from your house or the library or Starbucks or wherever you can get an internet connection. But virtual doesn't give you the same responsibilities as somebody that's remote, because we cannot count on those virtual networks, Comcast, Xfinity, whatever it is. For remote, though, we've specifically said that we have dedicated facilities with dedicated NASA networks, and those we can rely on. And so it's kind of also changed it's changed the whole paradigm of how do you approach something and how are you going to build it. And then lastly, your efficiency suffers in executing those activities. Now, this is not efficiency of doing work at home. What I mean is, when you are finally together, you have to use different things. You can't meet with everybody, so now you have to have a WebEx. You got to set the WebEx up. Well, my experience over the last 6 months is, Zoom has worked pretty well, WebEx and Teams. However, it's not uncommon to have issues with WebEx, Teams and all of it. And it just is. So I think it's become part of it. You can still get work done, but again, it takes you a little bit longer because you spent 10 minutes trying to make sure somebody had the right link, or they couldn't find the mute button, or there's some crazy feedback on the phone, right? Let's see. So planning forward, take a conservative path. build on it. Keep your reality with what it is now instead of hoping for something to change better. You can act now, and expect to change. Expect people to get sick, and expect to be able to deal with that. Come up with a plan of, if this happens, what do we do? And then really just communicate very effectively. So let me give you some concluding thoughts. I think how am I on time, Ed?
Let's see, we're at noon.
I'm right. I need to wrap up. Let me wrap up.
Yeah, go ahead. Maybe another 5 minutes or so.
No problem. Let me wrap up. All right. So all of that being said, what I want to show is, some years ago, the Palomar telescope was the largest in the world. And, you can look at how big it was and how, it was only 5 meters in diameter and it weighed, almost 500,000 kilograms. Just absolutely crazy. But then you have, 45 plus years later, you have, you have a larger telescope that weighs 1/100th of what the Palomar was. So, and it's, this telescope on the right here, the James Webb, is going in space, and it's going on a rocket. So all of those challenges aside, this is still where we're headed. So I just wanted some parting thoughts to share with you. Obviously, everybody's excited about, the successor to the Hubble and the most premier tool that is coming out. It is a one-of-a-kind observatory, right? And we are on target for the October 2021 launch. The protocols and COVID-19, again, have kind of forced us to reconsider how you deal with less people, what happens to your workforce, and how your CONOPS changes. So we're a year away from launch now. And what's exciting is we are just about to begin our launch rehearsal campaign. And it's the first of 6 rehearsals that simulate the early parts of launch and early orbit operations, and then also science operations, telescope alignment and things of that nature. And what happens is it starts in November, and then once February starts, it is every other month leading up to October, every other month, where hundreds of us, I told you it's over 600 people, we will come to the Space Telescope Science Institute and work around the clock. This first one we have in November, we're simulating real time. So launch is very early in the morning. We'll be there in the middle of the night, and we will run continuously for 72 hours to represent the first 72 hours of life. We do our first burn in that time frame, and some very key activities. So anyways, I definitely, I'm a graduate of APUS Space Studies. Dr. Albin was my instructor. So I just consider myself very lucky to be part of this team. And I really had, it was my pleasure to sharing some lessons learned with you. And if there's no other questions, I could take them. You can always contact me through the university or Dr. Albin. I'm more than happy to answer your questions.
Thanks so much, Carl. And we do have one question for you before we're running tight on time. Before we move on to Dmitry's presentation. The question is, with the track record of Hubble initially, and with NASA having to do the 4 or 5 service missions to get things up and running, are there any, because of the distance of the James Webb Space Telescope from the Earth and its inaccessibility relative to Hubble in Earth orbit, will there in the future be opportunities to go out to JWST and do servicing missions similar to what we did with HST?
Great question. The answer is no. It has to work the first time. It has to work correctly. The problem that Hubble had with optics is resolved on our telescope because our telescope has adaptive optics. Each of the mirrors can move to refocus and create a new prescription for the telescope. So that will never be a problem. But yes, getting out there, there's no vehicle right now that we have that can go out 1.5 million miles and come back. So maybe Blue Origin or SpaceX would do that in the future, but right now there is no there's no vehicle to go there and do anything with it. So.
Oh, okay, good point.
Keeps a little pressure on us.
My fingers crossed that everything will go well.
Us too.
And the backup, maybe Elon Musk's Starship can help out if need be. So excellent talk. Thank you so much. I'm so excited about the Halloween launch of this new space telescope. All right, moving along. We're going to shift gears to an Earth-based telescope at Apache Point Observatory, and we have the deputy lead astronomer at Apache Point Observatory in Sunspot, New Mexico, Dmitry Bizyaev. And just a brief introduction, I have to say I've been working with Dmitry since 2012, before I was program director of space studies. Dmitry not only is the lead astronomer at Apache Point, but he loves to teach, and he is an adjunct faculty member at New Mexico State University and also American Public University System since 2012. So we're really honored to have him on the faculty. And this is often the case with many of our part-time faculty members that work for us. They have cool and exciting space jobs elsewhere. And I'm jockeying to get Carl on board to teach with us as well. So look for Carl, hopefully as an adjunct faculty member in the future. Maybe once your schedule permits it after the launch of the Space Telescope. But Dmitry has been heavily involved in the Sloan Digital Sky Survey, and which is an exciting mapping project of the universe that we're going to hear about in his presentation today, called the Sloan Digital Survey, Current State and Perspectives. So I'll hand it off to you, Dmitry.
Thank you, Ed. Can I just push the button, share screen, and it will share?
Yep, do share screen, and then you should see your PowerPoint.
Do you really see it?
I don't see it. You may have to click on it, Dmitry. If you hit share screen, you'll see.
Oh, okay. I got what you mean. Yes, share. Yeah, there is another button here.
There you go.
Oh, really? Do you see it now? Because
we see it.
I don't have any feedback yet. Sorry. Okay. First of all, thank you for inviting me to give a talk. Yeah, I'm really excited to give it. And I'd like to begin not from this talk, because it goes from space to the ground, back to the ground. But I am ready to see Carl's presentation and to learn about Carl's career. And I think it should be somewhere in the, I don't know, on the APUS page, and it should show that APUS education really works. That's the really good example. I really glad to see that. So, but yeah, going back to presentation. So I'm going to briefly introduce you to the Sloan Digital Sky Survey. It's and this is really exciting time, a really important time for the survey. But I will not spoil it in advance. So I'll tell it in like about 10 slides. So just a quick overview of the survey itself. This is up to date. This is the largest systematic survey of the sky in terms of time and efforts. And it really, so kind of formally it started around 2000, but the technical observations, they started even earlier. So it's in business more than 20 years. And kind of key elements of success. It's pretty small telescope now, but that time it was not too much small. But the point is that the survey used dedicated 2.5 meter telescope, and a pretty good site and team specially dedicated to the project, team that works on this project only. And the initial goal of the project was to build a comprehensive three-dimensional map of the universe in order to understand what happens on large scales in the universe. Again, I did it again, sorry. Just a brief history of instrument, what it used. It used to be an imaging survey, but the imaging campaign has successfully finished 11 years ago. And right now the imaging camera is retired, and pieces of this camera can be seen in, for example, Smithsonian Museum or in Japan. It became set of souvenirs now. And right now working instruments are optical spectrographs and also the near infrared spectrograph that helps to feel bright time during the full moon. So all spectrographs are fiber fed, and this is kind of technology that allows, it's pretty unique. It allows to observe not one object, but up to 1,000 objects just at once. So it's kind of, people often say that this is not just a telescope, this is a data factory that produces data for astronomy. So basically this is the telescope itself, and this is so-called wind baffle that looks a little bit unusual, but it just protects telescope from stray light and from wind. And the fibers themselves, they're located in the bottom in Cassegrain focus. And this is so-called cartridge here. Cartridges are replaceable, and during the night up to like 10 cartridges are used. So basically up to 10,000 spectra can be obtained in a successful night. So just a little bit about this. This was kind of dark time project. It was the main motivation of the survey, but then we received a bright time project too. It's completely different spectrograph, high resolution near infrared, and it's cooled down to liquid nitrogen temperatures in vacuum. So the spectrograph itself is connected through a long fiber to the same port in the telescope. And it allows to use observing time even when moon is bright, very bright, and even if we have like a lot of stray light sources around us. So just a quick overview. We used to have a so-called classic survey. It was it lasts through the same parallel with the imaging campaign up to 2009. Along with the imaging, we have obtained spectra of 1 million sources, 1 million objects, mostly galaxies. It's sensitive. They're not local. They're around just a little bit closer than Z1, and quasars far away, much farther than Z2. So then we started to do so-called BOSS project. Yeah, I'll explain it later a little bit. But this project is dedicated to. First of all, it was an upgrade of optics and CCDs, of course. We cannot run the same detectors for 20 years, probably. It's only Hubble Space Telescope can do that, but not us. We are on the ground. So 1.5 million objects were observed more. And then up to 2020, there was extended Baryonyka Slate Sky Survey, extended BOSS survey. So finally, we round up to about 4 million spectra altogether, obtained for 20 years. And then that's that's the time to get some principal results. What did we get with it? And actually, the paper, it's in the bottom, but it was just just sent to a journal, to referred journal. But press conferences, they took place about a month ago, maybe even closer to that. So the results of the 20-year campaign of observing and probing the three-dimensional structure of the universe is that we came closer to about to under 1% of precision in many cosmological parameters that we can study now. And when I was student, the uncertainty, for example, of Hubble constant was about 50%. It varied, or even 100%, very easily from 50 to 100 kilometers per second to per megaparsec. But right now we know this parameter with pretty exciting precision. It's not 1% here, but all other parameters, they better understood right now. So the age of the universe right now, universe got older. In many textbooks, including those that we use in the classes, it says like the age of the universe is 13.4, I guess, gigayear. And right now we can say that's the universe a little bit older, but many other cosmological parameters that can be seen in this paper, when it will pass the review, they will be reported. And the report, actually this value agrees very well with the W map and Planck measurements. And and we can say, yeah, that our knowledge of cosmology has really advanced with respect to that we had 20 years ago. The main purpose of this survey was to measure dedicated distance in galactic distribution, so-called baryon acoustic oscillations. I don't want to go to technical details to it, but everything can be found in on the website of the survey, sdss.org, right here. So you can see here it's one of examples, but this signal you can compare just the measurements and the error bars, and this signal of baryonic acoustic oscillation right now is seen very well, and we can measure the standard rule in cosmology as an independent distance indicator with very high precision. So going forward about the Bright Time project, it's also exciting because the Sloan Digital Sky Survey 4, which is formally still going on, at least, well, it did yesterday, but not today. It started using 2 telescopes, because our traditional telescope that we use in the Northern Hemisphere at the Apache Point Observatory was accompanied by another one in Chile, in the south. This is Las Campanas Observatory, LCO, and the LCO has received a clone of the Apache spectrograph, the same cryogenic spectrograph in the near infrared with high resolution. And the main purpose is to map our Milky Way and to measure and probe as many stars as possible. And you see this map in the right lower corner. This is the pointings of the Apache instrument and observations of it. You see the green spot, for example, is a very important field right now in astronomy, so-called Kepler field, where many candidates and confirmed stars with planet were discovered. But the disadvantage of the Kepler instrument itself, that it doesn't analyze spectra, it doesn't understand what stars it look at. So the Apogee is really like companion survey for many Kepler stars. For the Kepler telescope and for the new test instrument and test mission. So this is kind of synergy that allows us to study the planets with much better precision, and to understand what stars harbor those planets. So and finally, up to date, the Apogee missions has received observed spectra of about 500,000 stars in the Milky Way, a little bit less, but of the order of magnitude like that. So, and with this Apogee survey, we can study because of higher resolution, it allows to measure not only general metallicity of stars, but it allows us to actually study the abundance of more than 20 elements, up to 25 actually, in those stars. It depends on signal to noise, of course. And I just list, well, some projects, some bright projects that I can remember, but actually the list of the projects, specific projects that are being run with the Apogee survey count up to like few hundred right now. And all teams that participate in the survey, in Sloan Digital Sky survey, they can bring up their own project and conduct it. So and it has a big potential of synergy with Kepler, K2 mission, with Gaia and TESS too. Just that's one of funny pictures here that shows a study of especially important elements that form human body and life on Earth. And we do see very well this elements in all stars. And by the way, this is the map, kind of artistic map of the Milky Way, and real map of pointings and studied stars during the Apogee survey. Oh, sorry. Okay, and one more survey that came in play during this SDSS-4 in 2014 is was dedicated to study relatively nearby galaxies with panoramic spectroscopy. So that's so-called three-dimensional spectroscopy, when we obtain not just a spectrum and at certain point of one object, but when we create a spectral map of galaxies. So we have X, Y, and spectral direction for each object and a bunch of information. So for this purpose, the optical fibers that used to, for the classic survey that look at center of certain objects, and for distant objects that just the whole object was in one fiber. These fibers were organized in so-called integral field units. Integral field units is like a head of fibers. And yeah, those fibers, they're just placed in the sky plane at certain object, and maps of spectra were obtained. And the spectral coverage is superior, is the whole optical range. Resolution is very good for studying extragalactic objects. And as a result, we have completed a lot of projects, and data being reduced, the final data being reduced right now. And I just list as an example a few projects here that can be run with this telescope too. With this survey too. So that's well, a wide range of project. The most exciting, for example, I think, is connection between the active galactic nuclei, the black holes at the center of galaxies, and the whole rest of the galaxy. And we do see this connection. Also, yeah, I just show an example here. That's object of my interest. For example, this is a galaxy. It looks like a plain galaxy in the imaging campaign. So nobody knows what happens there before we take spectra, or at least like long slit spectra. But here, the panoramic spectroscopy, it shows that this galaxy has gas and stars that counter-rotate. And actually, nothing is unusual with this gas. It's definitely inflow from the outer space to the galaxy, and then it starts forming stars and behave like a regular gas in the galaxy, except that it counter-rotates. So it's kind of one of projects that can be run with this data. And exciting news today that in September it was concluded that we have completed the SDSS-4 survey, and finally we got funds to prepare and conduct SDSS-5, the next stage of the survey. And finally, what we have done in SDSS-4, so we completed the cosmological project, and results are being reviewed in journals. There are about like 20 or more than 20 papers, with one main paper that I have shown before, but they summarize very specific cosmological results. So the Apache project, it has been finished too, and data have been reduced, and a lot of papers are being prepared too. And finally, the manga, with its goal to observe 10,000 galaxies, has completed its goals, has met its goals, and observed just a little bit more than this amount of galaxies, and data being reduced too. And the strongest point of the Sloan Digital Sky Survey is that all data after a short preparatory period, they go to the wide public. And the data in 2021, next year, all data should be released, all data that complete the SDSS-4 survey. So up to date, this is the total count up to date from 2020 of the papers, and the survey is very noticeable in the literature and in the reference journals too. So since we just finished SDSS-4 and started SDSS-5, this is a brief introduction to SDSS-5 here. So this new stage
Dmitry,
of the
we have just a heads up. We have about 4 minutes.
Okay, I have 3 slides.
Okay.
So it's so-called the mappers, and the mappers is designed and we observe the Milky Way with 4 million stars, and it will cover that all these gaps between the pointings, and we will study very efficiently. We will study the whole stellar populations, all stellar populations in the Milky Way galaxy. Black hole mapper is kind of time domain survey, and it will it will put the main attention to observing the black holes in nearby and distant galaxies. And finally, it's completely new thing, so-called local volume mapper that will map interstellar medium in the Milky Way and very, very nearby galaxies like Magellan Clouds, M31 and M33, for example. And the critical innovation for our survey is that we are going to obtain robotic fiber positioner instead of cartridges that are manually changed by observers. So it's about one year or even half year to obtain this to receive this robotic fiber positioner. So there is a website and information about this service there. I will not stop at them. It can be read there. And yeah, I put the SDSS-5 starts its operations today. It's not like, well, it's not in indirect phrase. This is literally today. So today will be the first technical night of the SDSS-5 survey, and hopefully it depends on funds. It will be continued to 2025. So there is an explanation on the website how to access data. And actually, since I have 1 more minute, I'd like to express an idea that, first of all this data and all these results, instead of observing with telescope, which is important too, but the data already prepared and reduced, and it can be further, they can be used to train students and to run real science projects. And I encounter with many students in 699 capstone class students come and just start thinking about their projects. It's not really good timing to introduce them to the data and make them use the data to run their own project immediately in this class, because there are only 4 months, and at least 2 months should be dedicated to write a draft and to hone it completely to a thesis. But we could have a special class. Just in this class, we can teach students how to use this public data from surveys. The public data already exists. SDSS is not the only survey that has public data released to public, but at least here there is an infrastructure of how to use the data, how to access data with SQL requests and how queries, and how to use FITS files, for example, and what is in FITS files. So a lot of science can be done, but we need a dedicated class for it. That's my opinion.
Excellent point. And as program director, I am going to follow up with you about this and how we can make use of the Sloan Digital Sky Survey in our classes. I may be picking your brains as adjunct faculty on how we can do this. Very fascinating presentation. We're on the home. We're a little tight for time, and so we're gonna head over to the next talk, and feel free to post questions in the chat. And if Dmitry can stop sharing your slide there up at the top, you should see stop share. There you go. But Dmitry can field questions. I had one about dark matter and and so forth. But let me transition over, because we want to stay on time. I just wanted to give a quick update on an asteroid project that we've been working on at APUS, and I wanted to share a few slides here. Let's do this. Okay, there we go. And let me move that out of the way. Let's see, there we go. All right, I am Albin, Program Director for Space Studies at the American Public University System, and I've been with the university since 2011, and we've been working with Dmitry since 2012. And we have a new project that is getting underway, the synthetic tracking of near-Earth and main belt asteroids or minor planets. And this is a project that actually at this point is utilizing 2 telescopes, the 24-inch plane wave, fully robotic telescope that you see on the left side with the SBIG digital camera that is operated by the American Public University System, faculty and students at the main campus in Charlestown, West Virginia, and also an 8-inch RASA 8 wide field astrograph, a celestron astrograph located in my personal observatory at the Deer Lake Astronomy Village. I'm based in Atlanta, and my observatory is 120 miles east of Atlanta in the least populous county in Georgia and second least populous county east of the Mississippi. So the skies are very dark. Earlier in the week, I was out there and the Milky Way was shining brilliantly. But the goal is primarily to do follow-up observations of asteroids, astrometric observations where and here you can see an example of a batch that was submitted to the MPC Minor Planet Data Center, where we compile our observations. This is a wide field observation at my observatory. The Minor Planet Center code for my observatory is W32, and that's located again in east of Atlanta in Crawfordville, Georgia, at the Astronomy Village, using the 203 millimeter RASA telescope and CCD camera. And here you see an example report that was accepted from observations, 63 observations that were taken in July of this year. I'll give you a feel for what we're doing. We're imaging, for example, a typical imaging run. This is some data in an example wide field image. The RASA can, with an ASI 294 camera, can give us a 3 by 2 degree field of view, a very wide field for survey work, observation work. There can be dozens of asteroids in that field of view. Typically, we take 2-minute exposures, 120-second exposures. And this particular observation run, that was done over a 3-hour period of time. So 75 images that we place into a new and very cool software package, Tycho Tracker software. It utilizes synthetic tracking and also the GPU game card capability in the typical PC, so it can process a lot of data, which, but depending on the speed of your computer and your GPU, can be in the range of 20 minutes to 2 or 3 hours to process that. So what we're doing is precision astrometry and submitting that data to the Minor Planet Center. And just quickly, we have a few minutes. We do the typical calibration of images, align and plate solve, and all of that is done through the Tycho Tracker software, which was developed by Daniel Perot, and observational astronomer. And you can, I believe it's at tychotracker.com, you can download this software if you're interested in synthetic tracking of asteroids. And the thing is, what it will do is it will stack those images to improve the signal to noise ratio of to be able to identify the movement of targets. And it takes advantage, as I said before, of the GPU video card to accelerate the process, the thousands of cores in your video card. So just example of the asteroid tracks here for the observation down at the lower left. You can see we actually identified 1,000 tracks in this data set from July 14th. And so what it will do is it will verify tracks and then allow you to add your observations to the current observation list for whatever asteroids or possible asteroids you have discovered. So it's detecting moving targets is the first step, and then it's acquiring accurate and precise measurements of those targets, and then compares them to Starr catalog, and then the measurements are generated by the Tycho software. And so you get residuals that are better than 0.5 arc seconds, which in order to submit to the Minor Planet Data Center, you have to have residuals less than 1 arc second. And here you can see an example of from the observations we made this summer. My observatory on the lower left side highlighted W2, and our residuals are less. It's being compared with existing observations. We can see those are in the 0.1 to 0.8 residual. So we do have that precision, which is under 1 arc second. And so that allows us to submit those observations to the Minor Planet Data Center. And we're just about out of time to do a demonstration of the Tycho Tracker software. However, there are plenty of videos if you're interested in this sort of thing. And this is something for American Public University students that we are going to have them involved in. And I'm going to share, let me see if I can find the website very quickly. Tycho Tracker, it's tycho-tracker.com. And you can learn all about that there. There it is. Okay, so I'll finish up by sharing the website you can go to. This is hosted by Daniel Perot, the author of the tracker. Synthetic tracking of asteroids has been around for a long time, but he's done a particularly good job where you don't have to have a supercomputer in order to process lots of data. And the idea is to do follow-up observations of asteroids, but also lots of potential, and discoveries have been made by other observers, be able to discover an asteroid. And the Minor Planet Center still allows you to name the asteroid once it's confirmed. So you can have your own asteroid up there in the sky. All right, we're running a little bit late. Feel free to reach out to Carl, myself, Dmitry. If you have any questions, you can reach me and I can filter those questions out to everyone. I'm ealbin@apus.edu. Be happy to answer questions. And thanks so much for attending our conference.